We now consider two typical examples of convex and concave functions, and then we take up two important questions. So first we can have a look at figure 9.17. Here we show the graph of function p, and here if I can write this, p of t is world population. It's written also here, world population in billions in year t. So we show the graph of function p, where p of t is the world population in billions in year t. And from this figure 9.17, we see that p of t is increasing, as in as we go on in time, the world population is surely not decreasing, it is increasing. And that just means in this case p prime t is greater than equal to 0. However, we also see that the rate of increase, that itself is increasing. So the slope of the tangent to the graph of the function, that slope keeps on increasing in this case. So this then this and then this. What we see here is that the slope of the tangent to the graph of the function is increasing as we go on in time. In other words, the rate of increase of the function, that rate is increasing. Or in other words, we can say that p of t is increasing at an increasing rate. That just means that when I say that the rate of increase, that itself is increasing, that means the slope of tangent to the graph, that is increasing as we go on in time. And that just means that if we take the derivative of the, and that just means that if we take the derivative of f prime t, in fact it is p prime t here, so here if we take the derivative of p prime t, that derivative is greater than equal to 0. Because of 2 points. One, we see that the rate of increase itself is increasing. That just means that the slope of the tangent to the graph of the function, that is increasing, as we can clearly see here. That just means that the derivative of p prime t is greater than equal to 0. Or in other words, p double prime t is greater than equal to 0. And that just means that this function is convex. Also, we can see here that when we go on in time, the rate of increase of the population, that itself is increasing. That just means we can think of it this way, that each year the increase in population, that increase becomes larger in figure 9.17. If we take the figure 9.18, if we take a look at that, this figure, let us say this figure shows the graph of function y of n. And what is this? This is y of n is the crop, that actually is the crop of wheat. When y of n is we have these many bushels of wheat, these are produced when we use n pounds of fertilizer per acre. So that's exactly a question, I think that's the same question we talked about earlier in this chapter, that when we put in n pounds of fertilizer per acre, how many bushels of wheat can be produced. So this is that figure, and it is actually based on the graph is actually based on the fertilizer experiments in Iowa in 1952, exactly the same question we talked about earlier. Now this function y of n, wherein y is a function of n, as in if we put in n pounds of fertilizer per acre of land, how many bushels of wheat can be produced. So this function, we see it has a maximum at n is equal to n naught, wherein n naught is approximately equal to 172. And that just means that if we increase the amount of fertilizer beyond n naught, that is going to actually cause wheat production to decline. Because here I see that the function has got a maximum at n is equal to n naught, which is around 172. So when you put in approximately 172 pounds of fertilizer per acre of land, you get the maximum production of wheat. In this case, we see that y of n, as in this function, we see is concave. Just looking at the way it is shaped, we see that it is bulging out the x-axis, and surely it is concave. But now let's understand why it is concave. We know that if n is less than n naught, and when I say it is concave, that just means that the slope of the tangent to the graph of the function, that keeps on decreasing. So in this case, as I said, first, number one, the function has got a maximum at n is equal to n naught. That means if you increase the amount of fertilizer beyond n naught, that will actually cause wheat production to decline. So the function is increasing till n naught. After that it is decreasing, and n naught is at n naught the function reaches its maximum. Also, we see that the function is concave. In fact, if we take a look at n less than n naught, if we see that n naught is around 172, like this, before that, as we keep on increasing n naught, so we move here till this time, as in we move till n naught, we see that the increase in y is less the larger is n naught. So herein what I'm trying to say is that as we approach n naught, this slope keeps on decreasing. That just means that increasing n by 1 unit leads to less increase in production of wheat, leads to less and less increase in production of wheat the larger is n naught. So as we keep on approaching n naught, yes, we see that the function is increasing. So when we move towards n naught, as we increase the number of pounds of fertilizer per acre of land, we see that the production of wheat is increasing, but the rate of increase is decreasing, as in the production of wheat is increasing at a decreasing rate. In other words, the larger is n, the larger is the number of pounds of fertilizer per acre used, the lesser is the increase in wheat production. And this is the time before we reach n naught. So I'll repeat this, that before we reach n naught, as n is increasing, y is increasing, but it is increasing at a decreasing rate. That means before we reach n naught, increasing n by 1 unit is actually going to lead to less and less increase in y the larger is n. On the other hand, if we go beyond n naught, now if we increase n, let's say now we go beyond n naught. Now if we keep on increasing n, there is going to be, I know that there is going to be a decrease in y, because now the function is decreasing. After n naught, the function is decreasing. But as we see here, in this case, the slope of the tangent, that slope keeps on decreasing. So it reaches, so it turns negative now. But we can think of it this way, that the absolute value of the slope becomes larger. So if we are considering negative values, but as we all know, I mean, if we compare -5 with -15, so I know that -15 is surely less than -5. The point to note here is that it is, the slope becomes larger and larger, and it goes on in the negative direction. What I'm trying to say here is that as n is greater than n naught, and now if you keep on increasing n, you are going to get a larger and larger decrease in y, the larger is n. So if you are going to get a larger and larger decrease in I, that means you are going to get, let's say, first a -5, then a -15, then a -20, then a -30. So you are going to get a lesser and lesser, you're going to get lesser and lesser slope of the tangent to the graph of the function. So clearly, even here, as you increase n beyond n naught, the slope of the tangent to the graph of the function, that keeps on decreasing. So in this case, the whole function is actually concave. That means as you increase n, the slope of the tangent to the graph of the function, that keeps on decreasing. So here we see that this is concave, precisely because this is the case here. Given all this, now let's take up two very important questions. The first question is that we have to examine the concavity or convexity of the production function y is equal to a k raised to the power alpha, let's say a raised to k raised to the power a, little a, wherein a is greater than 0, and this is the case. And the production function is defined for all k greater than 0. So if I have to examine the concavity or convexity of this production function, the first step is that I have to differentiate y with respect to k twice, in the sense that first I have to differentiate y with respect to k, and then I have to differentiate it again. And that will give me, so first I have y is equal to a k raised to the power a. I go for y prime first, which gives me a little a k a minus 1. Now I go for y double prime, that means I differentiate y twice with respect to k. So that gives me a little a minus 1, k a minus 2. Now, as far as little a is concerned, we know that this is the case. That just means if we take a look at this, capital A is greater than 0, little a is greater than 0, but little a minus 1, this I know is less than 0. That means this whole expression, a multiplied by little a multiplied by little a minus 1, this whole expression is less than 0. K I know is greater than 0. So this I know is greater than 0. If that just means here that y double prime is less than 0 for all k greater than 0, and that means hence I can write the function is concave. Sorry, the function is concave because y double prime is less than 0 for all k greater than 0. And if we want to take a look at the graph here, for the graph of y is equal to a k raised to the power little a, for little a being between 0 and 1, we can see this diagram, this one, figure 9.19, and we see here that you have the graph of this is the case and this is the case, and you can clearly see that the function is concave. On the other hand, if little a is greater than 1, then we have this case. So for that, again, let's get back to where I have written y double prime. Here I see that if little a is greater than 1, y double prime will actually be greater than 0 if little a is greater than 1. So here I can write that if little a is greater than 1, y double prime will be greater than 0, and in that case y is a convex function of k. In that case y is a convex function because y double prime is greater than 0. That's exactly what we can see here. You have in figure 9.20 capital A greater than 0, little a greater than 1, and you see that the function is convex, and you can actually see it in this figure. So that was one question. Now let me take up another question. Suppose that we have two functions, u and g, and let me say these are these, and both of them are increasing and concave. So these are increasing and concave. That means we have y prime greater than equal to 0, y double prime less than equal to 0. Also we have g prime greater than equal to 0 and g double prime less than equal to 0. In this case, we have to prove that the composite function f of x equal to g of u of x. We have to prove that this composite function, this is also increasing and concave. So what we now have to do is, for this, so we have to basically, given the fact that u and g are both increasing and concave, we have to prove that this composite function is also increasing and concave. So for that, what we do is we start with this composite function. We write that here. We write f of x equal to g of u of x. And here we are going to prove that this function is increasing and concave. For that, we have to take its first derivative and also its second derivative. Now obviously for that we are going to use the chain rule. If I take up f prime x, that is going to be equal to g prime u of x multiplied by u prime x. I know that both g prime and u prime are greater than equal to 0 because I know that both g and u are increasing, and that just means you have a product of two numbers that are both, you have a product of two terms that are both greater than equal to 0. That just means, so I know that this is greater than equal to 0, this is greater than equal to 0. That means f prime x is greater than equal to 0, and hence I can write f is increasing. So one part is done. We have proved that our composite function is increasing, and in fact what we see here is that I know that u of x is increasing, g of u of x, I know that u is increasing, I know that g is increasing. In other words, and that means g of u of x is also increasing. So what we are going to say here is that if we take an increasing transformation of an increasing function, that is increasing. We have an increasing function which is u of x. We take its increasing transformation, that is, we take g of u of x. And why do I say I take an increasing transformation? Because I know that g is also increasing. So number one, when I write in this case, given what we have analyzed till now, I can write an increasing transformation of an increasing function is increasing. For that, let's just take a look at, we are going to start with an increasing function which is u of x. Then we take its increasing transformation. So we take g of u of x. G is also increasing. That gives us this composite function, and this itself is increasing as what we have seen here. So that means we can say that an increasing transformation of an increasing function is increasing. It's a little bit of a tongue twister, but we have to understand why that is the case. Next, we prove that the composite function is concave. For that, we have to take up f double prime x. And that means we are going to differentiate f prime x with respect to x. So for that, let me write f prime x here. F prime x is equal to g prime u of x multiplied by u prime x. Now in this case, we are going to use the product rule, and for that, basically, for that we can write f double prime x is equal to the first function into derivative of the second plus second function into derivative of the first, and for that let me write g double prime u of x u prime x, and that just gives us f double prime x equal to g prime u of x u double prime x plus g double prime u of x u prime x, and that is squared. And now we have to take a look at what this is. I know that both u and g are increasing and concave. That just means in this case I know that this is greater than 0, and this I know is less than equal to 0. Also, we have this less than equal to 0 and this greater than equal to 0. So that just means this whole expression is less than equal to 0, and this whole expression is also less than equal to 0, and that just means that f double prime x is less than equal to 0. And this actually gives us one very important conclusion, that if I have this composite function, which is f of x, which is u of x and then g of u of x. So this I know is concave, and basically we started with a concave function which is u of x. We then went for an increasing concave transformation of this concave function. Why do I say that we go for an increasing concave transformation of this concave function? Because g is increasing and concave. We know that f of x is this, and I know that the second derivative is less than equal to 0. That just means that I can say here an increasing concave transformation of a concave function is concave. What we see here is that we start with a concave function which is u of x. We take its increasing concave transformation, that is g of u of x. G I know is increasing and g I also know is concave. That increasing concave transformation of this concave function is g of u of x, which I know is f of x, the composite function, and we have seen that that is concave. And that's why we say that you take up a concave function, you take its increasing concave transformation, that increasing concave transformation is concave.